Okay, so just to come back, all right. Thank you, Dante. So there is a hypothesis proposed. So potential hypothesis: the fibers of the nasal retina of each eye cross to arouse visual cortex to receive the same hemispheric visual field. The varying stimulus presented to the right side of the right eye interrupt the photochemical activity associated with the after image, therefore reducing its intensity. So that's interesting. I think what you mean is probably that when the input from here and also here is different, then the varying stimulus presented to the right side of the right eye. I mean, so you said the right, so maybe, yeah, I think it's okay. So right side stimulus projects onto the left side of the retina, so it gets processed like here, and then you are suggesting that it gets interrupted somewhere here or here. Is that what you're trying to say? Yes. Yeah, so that's actually plausible, but I don't know whether this is correct or not. But the reason I really like your proposal is that, in fact, this hypothesis that I presented is has been actually for a really long time untested, uncontested by the neurophysiologist. But recently, by my colleague in Vanderbilt University in US, suggested that there isn't a possibility. I mean, with their data, it's quite clear that even within layer 4, this kind of interruption already happens. So previously, people never doubted that there is no crosstalk within layer 4 of the V1, but it's no longer true. So what you're saying, maybe around here, there may be some kind of interaction going on, maybe also true. So that's a good point, actually. But I don't know, especially in human, we really don't know because nobody has done this kind of experiment. And it's not easy to do as well. All right. But that's a good conjecture. Great. And then let's move on. But the other possible, explanation is relatively simple. So maybe cortex has an after image component. So if you adapt to the color, then not only retina that adapts, but also cortical neurons also start to become adaptive. And so even if retina says that, oh, you should be seeing this after image of red and green, if the cortical area doesn't adapt, then it doesn't see it. That's the one possible hypothesis. And if you think about hallucination, dreaming, or various kind of illusion, then you start to see that what's out there. This is even the case for the lilac chaser as well, right? What's out there is not exactly the same as what you experience, and that's one of the most important lesson from this consciousness series. It's our experience is not veridical or mirror of what you see, what's out there in the world. Okay, so now I want to go to the next step of the discussion. What are the causal relationship between the neurons in V4, V8 and the color qualia? And the V4, V8 is the area that I'm going to explain next. Area V4, V8 is a part of the RE to meet visual areas, and it's likely to play a key role in color qualia. And evidence includes the lesion study, after effects, neuroimaging, and direct electrical stimulation. So the V4 locates within the hierarchy somewhere around here, right? So it's a mid-level areas. And then when there isn't a lesion around this area, what happens? So there wasn't a very rare cases, but there was some patient who had lost this V4, V8 area only on one side, right hemisphere here, okay, and nothing else. And then what happened to this patient is the loss of basically the color experience. So when he was tested with various color stimulus that was presented at the upper right or upper left or lower left or lower right, then what happened was that the discrimination between the red and some other color, like redness here versus orange or purple or something like that, that's easy to discriminate between at the upper right or lower left or lower right, but it's very impossible. You need like maybe 90 degrees skew, so that means that somewhere around here or somewhere around here you can start to say, yes, that's different from red. And the same goes for the green. Starting from green, she needed somewhere around here, like 100 degree of the difference to say that, oh, this is different from green. So it's a significant impairment of the color, but not other aspects. Or she also had some kind of a shape discrimination deficit as well. But anyway, how can we test this? That's a question that I wanted to pose to you guys. And the hints are that some slides in this week are the answer, in fact. Do you have any idea whether it's possible to test whether V4 or V8 reacts to the color after image or not? Separate from color itself compared to other areas of the brain. It's a bit difficult, so I'll just go with the answer slide, I think. That is this one. So what people did to solve this problem is the following. Wait. Might have done something. Yeah. So what they did was to use this image. So if you alternate, color at the bottom, like complementary color, blue and yellow, you don't see after image afterwards, right? But if you show constantly each of this color, then you see very strong after image. And the interesting thing is that during this alternation or steady state viewing, you continue to see 4 colors, right? So that means that if you use this alternating stimulation versus constant stimulation, then you can expect after image in the constant after the constant stimulation, but you don't expect after image after the changing stimulation, alternating stimulation. Yeah, there was an idea of the lesions or selective lesions, and that's actually also another interesting idea. If we can stimulate the brain, then you can make a virtual lesion. So that's a good idea. But we'll see what happens when you do this virtual lesions in a moment. Anyway, so if you do this alternating experiment, then what happens is something like this. If you look at the areas that responds to color, such as V4 and V8, then alternating color and a constant color evokes really strong activity here. It's a bit less for the constant color. And that's because constant color gives you adaptation and it starts to fade, okay? But the important thing here is that after seeing alternating color, you expect no color after image, and after constant color, you expect color after image, right? So if you subtract between those two, then what happens is the following. So here. So during this part, if you subtract this A minus B, then there's overall difference, minus 0.5% difference. That means that B minus A. overall, B is weaker than A because of the constant stimulation. But here is the point. C part, color after image expected part versus no color expected, color after image expected part D here. Then here, it's really huge response. And that's also the neural correlates of the color after image found in B4, B8, but not other places. So that's a very nice experiment published in 98 in Nature Neuroscience. And if you can propose something like this in the final proposal, then that would be also, probably full marks as well. Now, coming back to the original slide. So here is the answer, indeed, to the suggestion from Dante, in fact, that maybe we can do the virtual lesion experiment by stimulating the neuron here. And in fact, something like that was performed relatively recently here in 2017 and published in again top journal called PNAS. And there they had a patient, epilepsy patient, who needed to resect the foci of the epilepsy from the brain, but they didn't want to remove the parts of the brain that is involved in very important aspects of the life, like perception of face and so on. They implanted the electrodes in the brain areas and then wanted to avoid removing the area that is critical for face in particular. But for this particular patient, it turned out that it's quite interesting read. When they stimulated this particular pair of the electrode here, it's a bottom part of the brain. It's almost the same as a V4, V8 area. Then that elicited some color experience, not to remove the color experience, in fact. And here's the movie of this patient's report. You can look at that in the movie. Now, can you hear the sound? Can you hear the sound of this movie? Okay. In fact, it doesn't help for you probably because he talks in Japanese. So what he is saying right now is that this side of the box looks like rainbow. And then this is the recording of the brain. And then you see this, very strong artifact right now here, right? And then which is now removed. And that's the artifact is the part or duration where the patient was stimulated. Let's say here, okay? Once again. So that now stimulated, and then now it's over. And then he starts to describe his, experience. And in his case, he says that, left side of his face started to look like, rainbow. So, coming back. Remember, so this patient always described his experience of the color on the left side of what he was seeing, right? And that's corresponding to right side of his, brain stimulated in a B4, B8. And it's almost always a rainbow color. It's probably rainbow color because the electrode is much, much bigger than the small population of neuron that is necessary to invoke a specific color like red or blue or yellow. It probably stimulates all the types of neurons at the same time, and that's the reason why it induces rainbow color, but we don't know exactly why this is the case. So in summary, B4B8 is likely candidate of neural correlates of color qualia. And we started with this kind of discussion, in fact, from after image, where after images are coming from, and the lesion study and the electrical stimulation all converges to the fact that B4B8 seems to be very critical for color experience, including after image. But what is special about the neurons in B4B8 in generating color experience is not really explained by this finding. And that's something that we hope to see towards the end of the lecture series, but it's not easy to address right now. And that's a sort of the lecture part today. And then before I conclude, I wanted to also show some of the videos that suggest that there's lots of interesting things happening and also discovered over the years about our phenomenology. Not only this, a lilac chaser. So I want you to look at this video and then report what you see here. Okay. So up until here, probably you see flickering kind of, color, right? Okay, well, once again, initially flickering color, and then moving, and then color again. Did you notice anything weird about when the things are rotating? I'll play it again. Not quite. Observe it again. Color stops flickering. Yes, exactly. Do you agree? However, this is really weird, but if you look at the color directory, you can see that while it's moving, it's actually changing its color. Okay, one more time. It's probably you are fooled in double sense, right? If you are looking at the center, you probably see that motion is stopped. Motion freezes or silences the color change, right? But if you look at each individual color while it's moving, then it's actually changing the color at the same speed as when it's stationary. Like here, like this, and then, if you follow each of this. But as a whole, when everything is rotating together, then somehow we see everything as, same color, as stopping its color change. It's very weird, isn't it? Do you have any suggestion of why this happens? This was recently discovered, just 10 years ago. And it's called the motion silence illusion. So it's quite a new thing, so nobody knows. But some people may think that it is, another weird thing about the color, but it's not. So does it have anything to do with matching the speed of rotation to the speed of flashing? It's probably not. Even if the changing of flashing is much, much faster, as long as rotation speed becomes even faster, then you even can't see the faster change of the things. But anyway, I thought that it would be interesting to show that this also happens when it's when there was no color here. It's a black and white thing, but when it's moving, it stops changing, right? And also when it changes its size, like small to big to small to big, and then when it rotates, it stops changing. And also shape, from diamond to circle to square, when it moves, it stops changing. So there is something to do with our perception with the coherently things are moving. But nobody really knows exactly why this is the case. So that's you know, something to share with your friends or think about. I think this is really fascinating. Anyway, so with that, that's finished of the today's lecture. Is there anything else? Do you have any question about the lecture contents or tutorial or assessment? Fine. Then that's it. Thank you for attending for the class. See you.